The Maldives cave what the missing dive computers could reveal. The cameras may show what the divers saw. Witnesses may explain what was said before they entered the water. But the dive computers could reveal something neither of those sources can provide. A timeline measured in meters and seconds. How deep did each diver go? How long did each person remain at maximum depth? Did anyone begin swimming toward the surface? Did someone descend again after starting to leave? Did the computers issue decompression warnings? Did the 5 profiles remain together or separate during the final minutes? Those questions could transform the Maldives cave tragedy from a collection of theories into a technical sequence. But there is a problem. Despite claims circulating online, the individual dive computer logs have not been publicly released. Italian prosecutors have formally requested the computers, GoPro cameras, equipment, and supporting records held in the Maldives. The public therefore does not possess authenticated profiles showing exact depths, times, ascent speeds, selected breathing gases, or decompression obligations. What we do have are publicly reported figures. The cave entrance has been described as being approximately 50 to 55 meters deep. Some reports place the victims near 60 meters. Gianluca Benedetti was recovered separately, closer to the cave entrance. The remaining 4 divers were found together much farther inside the cave, in or near a dead-end section of the system. Recovery specialists suggested that the cave's layout and a sandbank may have contributed to the group entering the wrong passage. Those details do not give us a complete dive profile, but they allow us to ask a narrower and more useful question. If the reported depths and recovery locations are accurate, what should the dive computers contain? Today, we are going to reconstruct the kind of data investigators may be examining. Not pretend data, not invented numbers assigned to individual victims. A technical model based on the known environment, publicly reported depths, and established diving physics. Because the computers may eventually answer 4 central questions. Where did the dive become dangerous? When did the group lose its remaining margin? Did the divers attempt to escape? And were they still moving as one team when the emergency became irreversible? Let us begin with what a dive computer actually records. Most modern dive computers continuously measure ambient pressure. From that pressure, the device estimates depth. It also records elapsed dive time. Depending on the model, it may log maximum depth, average depth, water temperature, ascent rate, decompression ceiling, no decompression time, and selected breathing gas mixtures. Some computers record depth every few seconds. Others use longer sampling intervals. Technical models may record gas switches, oxygen exposure, and multiple decompression stops. Air-integrated computers can also display remaining cylinder pressure and estimated gas time. But an ordinary risk computer may not record gas consumption at all. That matters because viewers often assume a computer can show exactly when a diver panicked by detecting a sudden increase in breathing. Most dive computers cannot do that unless they are connected to a wireless cylinder pressure transmitter. Even then, a rapid reduction in pressure would not automatically prove panic. It could indicate heavy swimming. It could indicate gas sharing. It might indicate a leak. It could reflect a diver working against current. Or it could show a normal increase in breathing during a difficult exit. A dive computer records measurements. Investigators must interpret what those measurements mean. The first and most dependable measurement would be depth. At sea level, pressure increases by approximately 1 atmosphere for every 10 meters of seawater. At the surface, a diver is already under approximately 1 atmosphere of pressure. At 10 meters, the total surrounding pressure is about 2 atmospheres absolute. At 20 meters, it is about 3. At 30 meters, 4. At 50 meters, approximately 6 atmospheres absolute. At 60 meters, approximately 7. This has an immediate effect on breathing gas consumption. Suppose a diver normally breathes 20 liters per minute at the surface. At 50 meters, where the surrounding pressure is approximately 6 atmospheres, that same breathing pattern requires roughly 120 liters of gas per minute. At 60 meters, it becomes approximately 140 liters per minute. That is before stress, before swimming hard, before assisting another diver, before fighting through a restriction, and before attempting to find an exit in poor visibility. Now imagine a standard 12-liter cylinder filled to 200 bar. In simplified terms, that cylinder contains approximately 2,400 liters of usable gas measured at surface pressure. At 50 meters, a diver breathing at a surface equivalent rate of 20 liters per minute would theoretically consume approximately 120 liters per minute. 2,400 divided by 120 gives 20 minutes. At 60 meters, the same simplified calculation gives approximately 17 minutes. But neither number represents safe bottom time. The diver cannot plan to consume the entire cylinder. Gas is required for the exit. Gas is required for ascent. Gas may be required for decompression. A reserve must remain for an emergency. And in cave diving, gas planning must account for the possibility of helping another diver escape. That means the true usable penetration time may be dramatically shorter. If the divers entered the cave with single recreational cylinders and no meaningful redundant supply, the computers could show them accumulating depth and time while their gas margin narrowed faster than it would have appeared from the cylinder size alone. But again, we must be careful. Public reports have raised questions about their equipment. They have not provided a verified inventory of every cylinder, every regulator, every gas mixture, or every computer setting. We therefore cannot state exactly how many liters each diver carried. What we can do is demonstrate why even a seemingly full cylinder can provide very little decision time at 50 to 60 meters. The dive computers may reveal whether the group descended directly toward the cave. A rapid, steady descent to approximately 50 or 55 meters would suggest the deep entry was intentional. A more gradual profile with pauses at shallower depths might suggest that the group approached the site in stages. If the intended plan was supposedly limited to recreational depths, a profile continuing directly below 30 meters would become legally and operationally significant. Maldivian officials have said the recreational diving limit is 30 meters, while the fatal dive occurred far deeper. Authorities are investigating whether the group went beyond what had been authorized or expected. The computers may therefore help answer whether 50 to 60 meters was part of the plan from the beginning. Imagine 5 separate depth graphs appearing on a screen. At first, the lines descend together. 10 meters, 20, 30, 40, then 50. If all 5 profiles remain nearly identical, the group was probably traveling together. If one profile consistently leads the others by several seconds, that person may have been in front. If one diver remains shallower, that person may have been following above the group or hesitating. If a profile stops descending before the others, it could indicate a problem, a decision to turn around, or a different position inside the cave. But depth alone does not reveal horizontal location. This is one of the greatest limitations of ordinary dive computers. A depth of 55 meters could place a diver at the entrance, in the first chamber, or deep inside another passage that happens to be at the same depth. The computer does not know which direction the diver swam. It does not create a cave map. It measures vertical pressure. That is why investigators must compare the computer data with the recovery map, camera footage, and body locations. The location of Benedetti may provide one of the most important comparisons. His body was recovered separately near the cave entrance, while the other 4 were later found together deeper in the system. If his computer shows a different profile near the end, investigators might see evidence of separation. Perhaps his depth began decreasing while the other 4 profiles remained level. That could suggest he was moving toward the exit. Perhaps his profile rose several meters and then descended again. That might indicate an attempted escape followed by a return, or simply movement through uneven cave terrain. Perhaps his computer remained near one depth, while the others continued deeper. That could mean he stopped progressing with the group, but it would not explain why. A medical event could produce one profile. Gas exhaustion could produce another. Disorientation could create a different pattern. The data must be interpreted cautiously. Now consider the other 4 divers. Recovery divers found them together in a corridor or chamber ending in a dead end, approximately 50 to 60 meters underwater. Specialists suggested that the cave's layout, darkness, sediment, and a sandbank may have contributed to their entering the wrong route. If their computers remained at nearly constant depth during the final portion of the dive, that could be consistent with horizontal movement inside the cave. A person watching only the depth graph might believe nothing dramatic was happening. The line might appear almost flat, 52 meters, 54, 53. But horizontally, the divers could be moving farther from the exit with every minute. That is one of the most dangerous illusions in an overhead environment. A stable depth does not mean a stable situation. A diver can remain at 55 meters while swimming hundreds of meters into a cave. The computer shows no alarming vertical change, yet the distance from breathable air continues increasing. This is why the cave map matters as much as the profile. Suppose the group reached the first chamber at approximately 55 meters. They moved through a narrow passage toward a second chamber. Then they encountered a sandbank or obstruction that visually changed the route. Recovery accounts suggest they may have followed a passage leading toward the dead-end section where 4 bodies were found. If that reconstruction is correct, the computers might show a surprisingly ordinary depth profile. The tragedy may not appear as one dramatic plunge. It may appear as a long, flat line. The danger would be visible only when time is added. At 55 meters, every additional minute consumes gas rapidly. Every minute increases inert gas loading. Every minute extends the decompression obligation. Every minute spent traveling the wrong direction must later be repeated in reverse. If the divers realized they were lost 10 minutes after entering, they did not simply need enough gas for another 10 minutes. They needed enough gas to search, turn around, retrace the route, reach the entrance, ascend, and complete any required decompression. That is why the point of no return may have arrived before anyone visibly panicked. The dive computers may show when no decompression time reached 0. At approximately 50 to 60 meters, no decompression limits are extremely short. Exact limits depend on the algorithm, breathing gas, previous dives, and computer settings. But a diver remaining at those depths can quickly accumulate mandatory decompression. Once the computer displays a decompression ceiling, the diver cannot safely make a direct ascent without increasing the risk of decompression sickness. In open water, that is serious. Inside a cave, it becomes much more complicated. The diver must first find the exit, then travel back to open water, then ascend, then stop at the required depths. And all of this must be completed with whatever gas remains. If the computers use different algorithms or settings, they may have displayed different decompression obligations even when the divers followed similar profiles. One computer might call for a longer stop than another. One may have been set more conservatively. Another might have been configured for nitrox while the diver was actually breathing air, or the reverse. Investigators will need to determine the exact models and settings before interpreting the displays. The computers may also record ascent rate warnings. This is where a possible escape attempt could become visible. Suppose one diver began rising rapidly from 55 meters toward 45 meters. The computer might record an ascent rate alarm. That could indicate panic, but it might also reflect moving upward through the cave's internal structure. If a chamber ceiling rises sharply, a diver can ascend several meters without being anywhere near the surface. A rapid vertical change inside a cave is not automatically an escape. The investigators would need the cave map and video to distinguish between movement through the passage and movement toward open water. The same caution applies to descents. A sudden drop from 50 to 58 meters may look like the diver intentionally went deeper, but the passage itself may slope downward. The diver may have been following the floor, or an incapacitated diver may have sunk. The graph cannot explain intention. Now consider whether the computers could reveal gas consumption. If the devices were connected to transmitters, investigators may have cylinder pressure data. That could be enormously valuable. They might see pressure falling steadily during the initial descent, then a faster drop during penetration, then an abrupt acceleration during the final minutes. But even pressure data has limitations. First, investigators must confirm the transmitter was paired correctly. Second, they must know the cylinder size and starting pressure. Third, they need to determine whether the reading remained accurate. Fourth, they must consider gas sharing. If one diver began breathing from another person's regulator, one cylinder might empty rapidly while another's pressure stopped falling. A pressure graph could therefore reveal a gas sharing event. It might show one diver's supply reaching zero before the others. It could show whether the group's gas reserves were unequal. But there is no public confirmation that air-integrated logs exist. We must not invent a panic spike simply because it would make a dramatic video. A standard non-integrated computer would contain no direct breathing rate record. This is one reason the proposed phrase, "the logs show a panic spike," would be irresponsible unless investigators actually release pressure-linked data. We can calculate what stress would do. We cannot claim the computer recorded it. Let us model the effect. A calm diver with a surface consumption rate of 20 liters per minute uses approximately 140 liters per minute at 60 meters. If stress raises the surface equivalent rate to 30 liters per minute, consumption at 60 meters becomes approximately 210 liters per minute. At 40 liters per minute, it becomes approximately 280 liters per minute. A 12-liter cylinder beginning with 100 bar remaining contains approximately 1/200 liters at surface pressure. At 140 liters per minute, that is roughly 8.5 theoretical minutes. At 210 liters per minute, less than 6. At 280 liters per minute, slightly over 4. And those figures still ignore the need to preserve gas for ascent and decompression. This demonstrates how quickly a manageable problem can become fatal. A wrong turn does not need to last half an hour. At those depths, several minutes of searching under stress may consume the reserve intended for the exit. The computers could reveal the moment individual profiles started to diverge. That may be more important than the maximum depth. Suppose all 5 lines remain together for the first 10 minutes. Then Benedetti's line begins rising. The other 4 remain at depth. That would create one hypothesis. Suppose instead Benedetti's line stops changing while the other 4 continue. That creates another. Suppose all 5 lines show simultaneous rapid movement. That could indicate the group reacted together to a problem. Suppose the computers stop recording at different times. That might reflect battery failure, device damage, individual deaths, or simply the way each computer ended its dive mode. Investigators must also correct for clock differences. Dive computers do not necessarily share synchronized time. One could be several minutes fast. Another might use a different time zone. Some may have incorrect dates. Before comparing the lines, forensic analysts would need a common reference point. The entry into the water could serve as one. A distinctive depth change might serve as another. Camera footage could provide visual events that match changes in the profiles. For example, if the GoPro shows the group passing through a narrow restriction, analysts could identify a corresponding depth variation on the camera wearer's computer. That could help align the video with the numerical timeline. The 6th diver does not have a fatal profile to compare because she reportedly did not enter the water. That means the proposed idea of comparing the survivor's log with those of the deceased would be inaccurate. Her importance is as a pre-dive witness, not an underwater survivor. She may be able to describe the intended maximum depth, route, equipment, and expected duration. If her account says the plan was to remain outside the cave, the computers may show whether the group deviated from that plan. If she says the group intended to enter the cave, that would create a different legal and technical context. But the public does not yet have her full formal testimony. There is no reliable evidence that she is in witness protection, and her silence does not prove guilt or concealment. She may simply be cooperating privately with an active investigation. Now let us construct a hypothetical profile using only broad public figures. This is not the actual log. It is an educational model. Minute 0. The divers enter the water. During the first several minutes, they descend through 10, 20, and 30 meters. At 30 meters, they have already crossed the Maldives recreational depth limit. The surrounding pressure is approximately 4 atmospheres absolute. Gas consumption is approximately 4 times the surface rate. They continue toward 50 to 55 meters. At this depth, pressure reaches approximately 6 to 6.5 atmospheres. Gas consumption has risen proportionally. The cave entrance appears. If the team enters, direct access to the surface disappears. Minute 5 to 10. The divers move into the first chamber. Depth remains relatively stable. The computers may show nothing more dramatic than minor fluctuations. Yet decompression exposure is increasing. Gas is being consumed rapidly. And the distance to the entrance is growing. Minute 10 to 15. The team passes through a narrower section toward an inner chamber. Visibility may deteriorate as sediment is disturbed. If no continuous guideline was deployed, the team's ability to retrace the route may depend heavily on visual recognition. The depth graphs remain nearly flat, but the risk is climbing. Minute 15 to 20. The group reaches the area where the route becomes confusing. A sandbank or visual obstruction may make the correct return path difficult to recognize. The group turns into the wrong passage. They do not immediately realize the mistake. The computers still show approximately 50 to 60 meters. There may be no dramatic alarm beyond the decreasing gas supply and growing decompression requirement. Minute 20 and beyond. The passage ends. The group realizes there is no exit. They must turn around. Visibility may now be worse because 5 divers have disturbed the sediment. Stress increases breathing. Gas reserves fall faster. One diver may separate while attempting to locate the route. Another may begin sharing gas. The group's movement becomes less coordinated. This is where individual computer profiles could become different. But again, this is only a scenario. We do not know the actual entry time. We do not know how long they penetrated. We do not know their gas supplies. We do not know whether the computers contain pressure data. We do not know whether the emergency developed in this exact order. The value of the scenario is that it shows investigators what to look for. Did the profiles remain together? Was the bottom time long enough to create substantial decompression? Did one diver begin ascending? Was there a rapid final descent? Did any device record repeated depth changes consistent with searching? Were warning alarms active? What was the final recorded depth of each person? Did the computers continue logging after movement stopped? The recovered location of the bodies creates another important constraint. 4 people were found together. That suggests they remained connected as a group, or became trapped in the same area. Benedetti was found separately. That suggests separation occurred at some stage. But body position is not always identical to the location where incapacitation began. Current, buoyancy, and recovery activity can change final position. Equipment can become snagged. A diver may continue moving after another person becomes incapacitated. Therefore, the profiles and body locations must be compared rather than treated as identical evidence. The recovery divers' observations are especially valuable because they saw the physical environment. They described limited visibility, sediment, and a dead-end route that may have misled the group. Those observations support disorientation as a plausible factor, but they do not establish the entire causal chain. The computers could strengthen or weaken that reconstruction. If the profiles show long, nearly level bottom time followed by irregular vertical movement, that may fit a prolonged search. If they show a very short penetration followed by immediate separation, another explanation may be required. If Benedetti's profile moved towards shallower water well before the others, investigators may ask why he separated. If all 5 profiles stop changing at nearly the same time, a common event becomes more plausible. But even complete data may leave unanswered questions. The computer cannot tell investigators whether the divers felt confident. It cannot record an argument. It cannot show whether they saw the exit and rejected it. It cannot identify a hand signal. It cannot explain why the sixth diver stayed behind. It cannot reveal what the vessel crew understood about the plan. And unless it recorded cylinder pressure, it cannot directly show the moment gas became critical. This is where the GoPro, witness statements, and electronic communications become essential. The GoPro may show navigation and behavior. The computers may show depth and time. Messages may show planning. Permit records may show authorization. Autopsies may establish the medical cause of death. Equipment analysis may identify gas mixtures and mechanical problems. The truth will come from combining those sources, not from one dramatic graph. That is also why the public should be skeptical of anyone claiming to possess the complete dive profile without producing an authenticated source. The actual computers are evidence in active investigations. Rome prosecutors have requested access to them, along with cameras and other equipment held in the Maldives. Until those logs are officially released or described in a final report, we should not assign exact second-by-second movements to the 5 divers. We can explain what the data could show. We can model the gas demands. We can compare the reported depths with standard diving physics. We can identify which hypotheses the computers might test. But we cannot honestly claim to have reconstructed the final minutes from data the public has never seen. And that may be the most important conclusion. The absence of public logs is not proof of a cover-up. Dive computers recovered from a fatal incident are not ordinary personal gadgets. They are evidence. Their ownership must be established. Their data must be preserved. Investigators must verify their settings. The clocks must be synchronized. The profiles must be matched to the correct divers. The evidence must be shared between Maldivian and Italian authorities through lawful channels. And any final interpretation must survive expert and legal scrutiny. The numbers may eventually tell us whether the group intentionally descended to 60 meters. They may tell us whether one diver attempted to escape. They may reveal how long the group remained in the dead-end area. They may show whether the 5 profiles separated gradually or suddenly. They may reveal severe decompression obligations. And if air integration was used, they may show exactly how quickly the breathing gas disappeared. But the computers will not deliver a simple verdict. Data rarely says, "This person caused the accident." Instead, it creates a sequence. At this time, the descent began. At this depth, the group remained together. At this moment, one profile changed. At this point, the ascent became impossible without decompression. At this time, movement stopped. Investigators must then determine what human decisions produced that sequence. That is where technical reconstruction becomes legal investigation. The dive computer can show that a person reached 60 meters. A witness may explain why. The computer can show that one diver began ascending. The camera may reveal whether that person was searching for the exit or responding to an emergency. The computer can show extended time at depth. The equipment may reveal whether enough gas existed to complete the plan. The data can establish what happened physically. It cannot always establish responsibility. So does this change the need for the GoPro footage? In one sense, no. The computer logs may produce a precise timeline, but they cannot show the diver's decisions or the cave route. In another sense, the logs may be even more important than the footage. A camera can point the wrong way. A lens can be obscured by sediment. A recording can end early, but pressure data may continue recording in darkness. The computer does not need visibility. It does not need a clear camera angle. It simply records depth and time until it stops. The camera may show what the divers saw. The computers may reveal what their bodies were doing. Together, they could provide the closest possible reconstruction of the final dive. But until the authenticated data is released, we must remain inside the limits of the evidence. The known facts are disturbing enough. 5 divers entered a cave at approximately 50 to 60 meters. 1 was recovered closer to the entrance. 4 were found together in a deeper dead-end section. The recreational limit was 30 meters. The investigation is examining the planning, authorization, equipment, and decisions surrounding the dive. The missing computers may contain the timeline connecting those facts. So here is the question. If the dive computer profiles are eventually released, what should investigators publish? The complete raw data from all 5 devices? A synchronized graph showing the 5 profiles? Or only an official written reconstruction protecting the privacy of the victims? And one more question. If the computer data contradicts the most popular theory about the tragedy, will people accept the evidence? Or will the mystery simply produce a new set of arguments? Tell me what you think in the comments. Because the cave kept no written record, the divers could no longer explain their decisions. But somewhere inside those recovered computers, the final dive may still exist as a line descending into darkness.